Yeah. Okay. Everyone can hear me, right?
Yes, sir.
Yes, sir.
Yeah. Great. Okay. So let's march along in our um, efforts to understand the Fourier analysis. So a quick recap, we looked at the LFP data. That was a few classes ago. This is the evoked response. We asked the questions. We're looking for oscillations in the LFP and if the power of frequency change with time. So that led to the Fourier analysis. Um, in one class, we just talked about systems in general, in particular time variant and linear systems, LTI, and the fact that they can be well represented when understood if you understand how they respond to an impulse function. So we did all of this both in continuous and discrete domains. That was one class. And then in the previous class, we looked at complex exponentials and why they are so useful. And the answer is that if you give a complex exponential as an input, you get a complex exponential as an output from a LTI system, where just the output is multiplied by some number, some complex number, which is given like this. Okay, and therefore, if you can represent any signal as a sum of complex exponentials, you can very easily find out what the output is going to be. If the system is LTI, all you have to do is know these H. How a complex exponential as an input is transformed or basically just multiplied and with some amplitude and shifted by some phase. So if you know this, you will be able to find the output of any input xt. So the question is, can I then represent my signal as a sum of complex exponentials? Okay, and that is the Fourier analysis. So we started out by talking about the Fourier series, which is a continuous periodic signal. How do you represent that? If you have got a signal which is periodic, this is what that means. Then we consider a set of complex exponentials written like that. Here, notice that this t comes here. So this fundamental frequency is omega naught, 2 pi by t. And the complex exponentials are just multiples of omega naught. So it's omega naught, 2 omega naught, 3 omega naught, and so on. And turns out you can represent any periodic signal as a sum of complex exponentials given by this formula, this, and we found out what AK should be. Okay, and AK is just given by this formula here. So together this forms what is called the Fourier series analysis. This is called actually the synthesis equation. The first one here, it just means that given the coefficients AK, how can you synthesize the signal back? And this is what is called the analysis equation, where given the signal, how can you find the coefficients? Okay, so if I give you the signal xt, all you have to do is integrate like this over a period of 2t. It could be any period of t. It turns out this works out well because this signal is periodic. And you get your AK. Okay, so and then if you have all the AKs, if you use this formula, you'll get back xt. Okay, so there is a little bit of complexity here, that if you have the coefficients AKs with you and you say I'm going to sum it up like this, am I going to exactly get back xt, or can it be slightly different? Okay, so this is a more involved topic. I'm not going to go over this. But remember what I had told you a while back, that if I've got a signal xt and another signal x1t that just varies at one single point, let's say. Okay, so let's say xt is 0 everywhere and x1t is also 0 everywhere except at 1 where it takes some value. So actually because the difference is at an infinitesimally small point, the energy of the difference xt minus x1t whole square dt, if you integrate it, it's going to be 0. Okay, and then this is what is called mean square convergence, which means that x1t should be considered same as xt because the difference of their energy of the difference is actually 0. So this is where the convergence of this comes into the picture. There are some extra conditions that xt needs to satisfy in order for this stuff to work. Okay, so in other words, you can come up with an xt for which even if you get these AKs using this formula, when you try to resynthesize this back, it may not turn out to be this. Okay, so this is more complex stuff that I'm skipping for this course. So this relates to the convergence of the series and some conditions called Dirichlet's conditions that are sufficient to ensure that the coefficients once found will give you the signal back up to mean square convergence. And there are different forms of convergences also depending on how the signal behaves. This is more complex than what we can handle in this course. But just wanted to point this out because it's a topic which is addressed to some extent in Oppenheim and Wilsky as well. And it's in general something that, everyone should be aware of. Okay, but we are not going to talk about it. So as far as we are concerned, you can just assume that this is the analysis and synthesis pair. If I've got any signal, I can always decompose a periodic signal. I'm always going to be able to decompose it as a infinite sum of complex exponentials like so, where AKs can be obtained by integrating the signal with e to the power minus jk omega naught t. Omega naught is just 2 pi by t. Okay, so we did a few examples. If you have sine omega naught t, this is how it looks like. Sorry, here you don't even have to integrate. You can just read off the coefficients directly. So a1 is 1 by 2j, minus 1 is minus 1 by 2j. Everywhere, every other coefficient is 0. Then we also look at a periodic square wave pulse, and we worked this out, and we found AK equal to this formula here. So you can actually plot it even if you want for different values of T1. Okay, so there's a signal is T1 and then is periodic after T by 2. And actually turns out this can be thought of as samples of, just one second, move this around. Yeah. Samples of a continuous function, which is given by this here 2 sine omega 1 t by omega. It's a continuous function of omega, and you're just sampling it at k omega naught, where k goes from 0, 1, 2, 3, 4, 5, 6, 7, 8. This comes right from this formula. Okay, I should mention that the next couple of classes, at least before we get back to the signal, we are going to basically be doing the development in this way only. And this integrating over exponential, this is a common thing that will keep coming. But there will be slight variants depending on whether the signal is periodic and things like that. So this can get very confusing. Okay, so there's no easy way out. I mean, people who do this as undergrad spend a couple of semesters doing this. So I'm trying to compress it in 3-4 classes. So it can go out of, you can get really confused. So please stop and ask questions anytime you have one. There are no stupid questions. Whatever is confusing you is probably confusing your colleagues as well. And also please very carefully read Oppenheim and Bilski. Otherwise, it's very easy to get lost in this. Okay, so then in the previous class, we had talked about properties of the Fourier series, and we had talked about some of these properties like time shifting and linearity and so on. Conjugation is another one. So here, if your signal has some resemblance with the original signal, its coefficients will also have some resemblance with the coefficients of the original signal. So if I take the conjugate, it just becomes the negative coefficient with a conjugate. This is what we proved in the last class. This is where we were in the last class. Okay, any questions or can I move on now? Okay, so looks like everyone is happy so far. Either that or terribly confused, so not asking anything. But as I said, I can't see anyone, so you'll have to ask if something is really confusing you. So today I'm going to talk about first up a very important property which keeps coming in many forms when we talk about Fourier analysis, which is duality between multiplication in one domain and convolution in the other domain. Okay, here also if I convolve two signals in the time domain, turns out in the frequency domain it's the same as taking the product of the coefficients. So Fourier analysis converts convolution to products and products to convolution. It's an exceedingly important property. So for example, if I say I'm going to use a filter, so essentially what that means is I convolve the signal with the filter. But in the frequency domain, it just means multiplying the signal with the Fourier transform of the, or in this case, Fourier series of the filter. So if the filter is an ideal sort of filter, where so I've got a signal like so, x of t, and the filter, let's say, looks something like this, h of t. And suppose in the frequency domain, xt has some shape. This is x of omega. Sorry, I'm right now talking about Fourier transform, but it holds for other type of signals also. So it doesn't really matter. And suppose h of omega is like this. It turns out it's going to be a sinc function. Not drawing it very well, but so in the frequency domain, the point I'm trying to make right now, we'll get to this all of this later also. It's just a product of this and this. So it will just wipe out everything else other than this little bit. So the convolution in the time domain translates to a product in the frequency domain and vice versa. It's an exceedingly important property. So this one I'm going to prove today in class, and we will see that it very nicely relates to this also, which is another very important property. Okay, so let's see the proof. Let me discard this here, and I'll try to prove this on the board. So remember, I've got a signal x of t, which is a periodic signal with a period of t. and I've got some coefficients AK for this. Okay. And similarly, I've got a signal y of t, which is also periodic in t, and the coefficients of are bk. So the question is that if I take the product xt yt, what are the coefficients, let's say ck, are they somehow related to ak and bk? Okay. So let's work this out. Let's see. So remember, how are AK and XT related to each other? XT is just the sum of all Ks like this, J, K, omega naught T. Okay, where omega naught is 2 pi by T. Right? So this is the synthesis equation. And similarly, you will have it for this also. Where now AK is given by 1 by t integral over t xt e to the power minus j k omega naught t. Correct? This is the Fourier series expansion. Nothing magical here. We just did that in the last class. So I will say, okay, let me try to find out what ck is. So ck by definition here is just integral of xt yt e to the power minus jk omega naught t. Right? I've just put the signal here, which is the product of xt and yt. But now what I'm going to do, I'm going to put these xt as this full expansion. So this is going to become summation over, so I'm writing k here. So this I'm going to put some dummy variable m and write am e to the power j m omega naught t. And let me do some other dummy variable L here. And this is going to be BL e to the power JL omega naught T. Then this one comes here, e to the power minus JK omega naught T dt. Okay, everyone okay with this? All I have done is just put the values of xt and yt in terms of AKs and BKs. That's it. But now I see that these are just products of two sums, so I can look at this as a double summation. Okay, so I'll have the integral here as well, and I will just can write this as AMBL e to the power j. What is it? J omega naught t, and this will become m plus L minus k dt. Okay, I'm just taking all these exponentials together. It's a double summation now. So this is what I get. Is everyone okay with me with this so far? So now who can tell me what is the integral of this thing over one period of t?
If m is equals to L minus K minus L, then it is 1, otherwise 0.
Very good. So this is the same logic that we have done in the previous class. Actually, all of Fourier analysis at the end of the day, turns out it actually can be understood based on this thing here. That if I integrate a complex exponential, if I integrate something like this, the integral is 0 whenever k is not equal to n, because this becomes like cos k minus n omega naught t plus j sine k minus n omega naught t. And as long as it's non-zero, 1 cycle or 2 cycles or 3 cycles, doesn't matter how many cycles, they always integrate to 0. We did that in the last class, right? But when k is equal to n, then this is just t. Okay, at the end of the day, we'll see that this thing keeps coming up in different ways, and this is the only important thing that needs to be understood for us to solve things. So here, actually, even though it looks quite complicated, it is, if I, so see, this integral is over t, am and bl are independent of t, the t is only sitting here, it's only here. So I can bring the integral inside of this and write it as a double summation of ml am bl, and then the integral, this thing I can write together, of e to the power j omega naught, what was it, j omega naught t m plus l minus k dt. And turns out this thing here inside is 1 when m plus l is equal to k, but otherwise it's 0. So this thing is nothing but summation ambl this. This was the key step. Is everyone okay with this? Otherwise I can repeat this. Okay, I'll take this as a yes. People are with me. So now I'm going to just rewrite it in a slightly different way. So AM, the summation here is over L. So AM can come out here. It's over L, BL, delta function of L minus K minus M. It's just, put it in this way. It's the same as this. L minus K minus M I've put under brackets. Now, if you look at this summation here, delta function is always 0 unless L is equal to K minus M. For all other values of L, it is 0. So this thing is nothing but so I have actually proved, this is probably the hardest thing to prove here, that the product in time domain becomes convolution in frequency domain. Okay, are people still with me? Say something, guys.
Can you repeat the last step? I missed it.
Going from here to there.
Yeah.
So this is see, delta of L minus delta function of whatever n is 1 when n is 0 and 0 everywhere else, right?
Yeah.
So that's the definition of a delta function. So I'm summing over L here. L goes from minus infinity to infinity. But this delta function is going to be 0 for all values of L except when L is K minus M. Because this thing has to be 0. The delta function of 0 is 1 and delta of n is 0 for n not equal to 0. That's the definition, right? So I'm summing over, it's like B1 delta 1 minus K minus M plus B2 delta 2 minus K minus M and so on. But the sum has all zero terms because delta function is zero everywhere, except when L happens to be k minus m, because then this thing inside is zero. Same
Yeah.
idea
Yeah.
here,
Got
that the integral is going to be zero unless this thing is zero. So this entire sum is just b of k minus m. K minus m, k minus m, that's the term is preserved, everything else is killed. Does that make sense?
Yeah, yeah.
Yeah. Okay. So this is a killer property. Convolution is hard to do. It's a difficult operation, but in the frequency domain, it's just a product. So it's a piece of cake. In a bit, we will also see the converse one, where the convolution in time domain becomes a product in the frequency domain. Okay, so right now we have done product in time domain becoming convolution in frequency. We'll do the converse in a bit. So here's another very interesting property. Let me just start from here. Xt, yt and akbk. So xt is given by this formula and ak is given by this formula. So now let me ask you that I've got xt and it's got its ak's. And suppose I make yt equal to x star of t. It's the complex conjugate of x. So what did we learn about the conjugate of, the coefficients of yt? What was that? We had looked at the properties. We did that in the previous class, but I'll go back because, things are happening fast right now. Do you guys remember this? We proved this in the last class, that if I take the conjugate of a signal, what I end up getting is the flipped time axis in the frequency axis, the conjugate at minus k. Okay, so it's going to be a at minus k with the conjugate. That's the relationship, and we did that in the last class. So now I'm going to ask that what is the, so this is just what is the kth coefficient of xtyt. Okay, and you will notice that it's just given by this formula here. K But what we just proved that this is also a summation of am p k minus m over all m's. It's a convolution as well. This is what we had just shown. Correct? Right?
Yes, sir.
So now, so now I'm going to look at the zeroth coefficient. So what is that? Zeroth coefficient is just this. And xt multiplied by x star t. Remember, so xt is a e to the power j theta, and then x star t becomes a e to the power minus j theta. So the product is always a square. Okay, you can also do it as, if this you write this as p plus iq, then this is going to be p minus iq. So the product is always p square plus q square. So the product of a signal with its conjugate is always a positive real number, which can actually be written as this. xt, the mod here, and you square it. The mod here is just a here. So this is mod plus some phase. But when you do the conjugate, the mod is preserved, the phase is reversed, the product wipes out the phase, and you get a number here. It's not a complex number. This is now a real number. What is that? This is the integral is over t here. What do I get here? The zeroth coefficient, when I put k equal to 0, this is what it is. But now remember that b of m is just a of b of k is just a star of minus k. So b of minus k is just a star of k. So this is actually okay. So the integral of the signal after taking the mod and squaring it and integrating over one period is the same as looking at the modulus square of all the coefficients and summing it up. Is this fine? Is the proof okay with everyone?
So this only occurs with on the first period of the frequency.
No. So the frequency axis is not periodic. So this is a case where your time domain is periodic. So the signal is periodic in the time domain. But in the frequency axis, the k axis here, it is discrete. And it keeps going there from minus infinity to infinity. If the signal is real, then these coefficients have some symmetry property, but otherwise for a generic signal, it could be anything. This is a complex signal. The periodicity is only in the time domain. It repeats after t. In the frequency domain, it's not periodic.
Okay.
So you have to sum up all the coefficients from minus infinity to infinity. But if you sum the square of them, what you end up getting is the same as the signal squared and integrated over one interval.
So at one interval, you would get this, right?
Yes.
Overall,
If the signal is periodic, you can't integrate it over the entire time domain because then you will trivially get infinity.
yeah. Got it.
Right? Okay, so is this fine with everyone? This is called the Parseval's theorem, and this is of huge importance in our development of Fourier analysis. If this is fine, I'll move back to the main presentation. If there are questions, please ask now. Okay, so let me go back. So this is what I was mentioning. This is the Parseval's equation. The integral, I think I have it on. Yeah. So Parseval's relation relates the signal here in the integral over time domain to the sum of the coefficients in the frequency domain. Now, turns out you can think of xt squared like the mod squared like the energy of the signal. Okay, so the left hand side is the average power in one period of the periodic signal. So this whole integral is the energy of the signal over one period. And turns out, and this you can think of similarly as the energy in the frequency domain. So the total energy of the signal can either be obtained by integrating the signal over one period in the time domain, or in this case, in the case of Fourier series, summing over the energy in the frequency domain. Okay, and it turns out this holds even for Fourier transform, which we will cover in a bit. And later we will see that we can actually consider this as a way to define a probability distribution function whose the function depends on this energy. So essentially, if you then look at mod of t squared over E, which is where E is the total energy. This is now a probability distribution function. It tells you how the energy of the signal is distributed over time. Okay, this will integrate to 1, it's always 0, it satisfies all properties. And likewise, in the frequency domain, we will be talking about the distribution of energy over frequency. The Parseval's relation actually relates the two and says that at the end of the day, you are just looking at the total energy, which is given by this formula here. Okay, and you can compute it either by looking at the energy in the time domain or in the frequency domain. When we look at power spectral density later, it's basically just this. It's just the, well, we'll get to the PSD in a bit, but at the end of the day, the fact that the energy of the signal can be obtained by either integrating over time domain or in this case summing over the frequency domain, and later we will see in for Fourier transform integrating over frequency domain as well, is of huge implication. It sort of relates everything in a very nice way. So that's why I wanted to spend more time on Parseval's theorem. Okay, this theorem just boils down from what I proved in that Jamboard a while back. Okay, this is okay with everyone, right? So now I'm going to move on and talk about so we are done with Fourier series. We're done with Fourier series. The signal is periodic. The representation in the frequency domain is discrete. You don't have, some value at all frequencies. It's only at discrete points given by AKs. Okay, but you need an infinite number of such points. This will just keep on going and going from minus infinity to infinity. So you'll end up getting representations that look like this. It doesn't repeat in the frequency domain, but the signal actually repeats in the time domain. So we're done with this. Now, very quickly, we are going to talk about the discrete version of the Fourier series, which is called the discrete Fourier series. And this is for discrete time periodic signals. Okay, so we are now looking at signals that are in discrete time. So I define it like so, and like this. And it being periodic means that if I add some number n, then it's the same as this. So x of n is equal to x of n plus capital N, which is equal to x of n plus 2 capital N, and so on. And now I want to know whether I can represent a discrete periodic signal as a bunch of, unit length complex exponentials like before. So I say, okay, let me do that. So I define now phi k n, this is instead of t now n, as e to the power j k omega naught n. This is exactly the same way what we had done in the continuous case, except that we had a t there. Now we have an n here. Okay, and omega naught is 2 pi by n as before. But now notice something very interesting. This is actually the key difference looking at the signals in continuous versus discrete domain. Notice that unlike previous time where I had an infinite number of complex exponentials, now I have only n distinct complex exponentials because this relationship holds. Okay, so this is very important. Look, n here, unlike t, which was a continuous signal, this is discrete. Right? So, sorry, not n here, sorry, this k here. So if I add k plus rn, what do I get? I get e to the power j k plus rn 2 pi by n n, which is e to the power j k 2 pi by n n multiplied by j to e to the power j rn 2 pi by n n. This gets cancelled out, and this is what? It's a 2 pi here. What is e to the power j 2 pi?
One.
1, right? Cos 2 pi plus j sin 2 pi. Yeah. What is e to the power j 4 pi? They're all 1. It's basically looking at a vector that keeps coming back if you do full revolutions here. So then if I add this any multiple of Rn, I'm going to get back the same thing as before. This is 5k and this is just 1. Okay, so unlike my continuous discrete continuous periodic signal that needed an infinite number of coefficients, for a discrete periodic signal I just need n coefficients because the remaining ones are just going to be the same as these ones. So in the frequency axis, now the signal is going to be periodic again. So I only need one period in the frequency domain as well. Since the sequences phi, k, n are distinct only over a range of n successive values of k, the summation in 3.87 need only include terms over this range. Thus, the summation is on k as k varies over the range of n successive integers, beginning with any value of k. So we indicate this by expressing it like this. This means that I can represent by my n just by summing over k distinct phi k's. And then I'm done. So I actually need only a finite number of terms on this side as well to get to this. Okay, this takes a while to understand, but this is actually key for understanding the future, discrete time Fourier series and discrete Fourier transform, which we'll get to. They all rely on this fact that unlike your continuous time domain, in the discrete time domain, it becomes periodic again. K plus Rn is the same as k. So the coefficients again start repeating, just like the signal here. Okay, so in the continuous domain, the time domain was periodic, but the frequency domain was not. In the discrete version, they are both periodic. So we can only need to worry about one period. Okay, so now we can ask, okay, how are we going to find the AKs? And turns out the formula is very similar like before. All we have to do in this case is, so this is the analysis, the synthesis equation which is similar to what we had before. But now the question is, how do you find a case? A case will be given by this formula. Previously, we were getting a case as an integral. Now I'll get it as a sum. Why is this holding? Let me show you the proof. It's written right here. Remember what I had done earlier? I had taken in the previous case. Let me just show you the previous case where I had proven this. I started out by saying, okay, I'm going to represent it as a case, and let me try to find the a case. I multiplied it by e to the power minus j n omega naught and integrated. And the integral wiped out this for all values of k's, n's except k. I'm going to use a similar logic now. But instead of multiplying by this and integrating, I'm going to do a sum. That's the only difference. So let's see what I'm doing here. So I say I want to find my a case. So I take my signal xn, which is given by this ak given by this formula. So xn is given by this formula. I multiply it by e to the power minus jr 2 pi by n, and then I sum it like this. Okay, so what are we trying to do here? Just to make everyone clear here, we are trying to find out how to get a case. I want to find out this equation. Instead of integrating, which I was doing before, I am instead doing a sum here. So this one gets now k from here and r from here, and it's a double summation. First summation coming from here, the second one is just coming from there. Okay, let me know, this is a little bit probably confusing, but let me know if you are losing this. The concept still remains the same. Earlier I was telling you that if I integrate e to the power j omega k t dt, because this is a cosine for any any number of cycles or any value of k, the integral is always 0, cosine and the sine. So this thing is 1 when k is 0 and 0 otherwise. Here it's a similar concept. Just the difference is that the summation that I'm looking at is now summing up vectors that regularly span this 2 pi axis. So the sum is always 0. Okay, this is the discrete equivalent of this continuous version here. Just look at this. Okay, so what I'm doing is e to the power jk 2 pi by nn, and I'm looking at sum of these n vectors. So these are the different vectors that I'm talking about, and this sum is always 0 unless you've got k as 0 or some other multiple of n, in which case they're all trivially 1, so that summation is n. Okay, and here that's what I'm doing here, that this, when I take this double summation and I take this ak out and look at the single summation of this thing is just going to be equal to 0 for all values of k, except when k is a multiple, k is r. So therefore, this sum is just ar multiplied by n. So this is just ar multiplied by n, and therefore ar is just 1 by n multiplied by this thing. So I have proved that in a discrete Fourier series, this is how this formula is what will give me the coefficients. So this is the discrete Fourier series synthesis and the analysis equation, which is the exact counterpart of the Fourier series for continuous domain. Okay, did I, does this make sense?
Sir, again a dumb question. Here in the summation n equals to n e to the power k e to the power j k r k minus r, that term gets converted into a r n, right?
That's right.
The remaining part remains the summation of k.
Yeah, yes. So yeah. Tell me. So this
So the
becomes this whole thing becomes ARN. This whole thing. This becomes a delta function, right? So this thing is this, and then when you take this summation, it will become ARN. So the whole thing becomes ARN. Not just this. This is like the delta function. It looks complicated, but this is exactly backtracking to this concept here. Nothing, it's exactly this concept applied in the discrete domain. Okay, so this thing, the first one, using this formula here, is this okay? This is fine with everyone, right?
Yeah.
When k is 0, then these are all ones. So you get n, summation of n vectors. They're all vectors lying like this. So the summation is just n. Likewise, when it is n or 2n or 3n, even in this case, these are all ones. But in all other cases, they would be something like these, so n vectors, and they add up to 0. Much like the integral was adding up to 0. If this is fine, this inner integral is just n times the delta function of k minus r.
Correct.
Right? And then when I take this summation, it only takes the rth value, so it's just ARN.
Correct. Got it.
Okay. This is complicated stuff, guys. So, just others are fine with this? Is this okay?
I have a question in the last slide, basically in the cyclicity.
Yeah.
So when we have 2 pi r n equals, when we have e power minus I, 2 pi r n is equals to 1. So I have a slight doubt that though I can understand 2 pi r is equals to 1, but what about n?
Yeah, so that's what we're looking at k here, right? For different values of k. So when k is 0, this whole thing becomes 1, irrespective of n.
No. N? Why?
When k is 0, this whole term is just 1. It's e to the power 0. It doesn't matter what n is. So I'm just adding 1 n times. That's why I'm getting n.
Okay.
Okay. So otherwise, you have to look at this e to the power j k 2 pi by n as some vector. If k is non-zero, this is some vector, right? And then n equal to 2, this is, the vector is, the angle is changing, and then 3 will change, 4 will change, and you do all these vectors, but the sum will always be 0. Okay, so this is one vector, which let's say is this, and then when n is equal, this is for n equal to 1, So right, so here's the n. So for n equal to 1, this is one vector. When n is equal to 2, you're just multiplying the angle by 2. So whatever it was, it got, the angle is changing, but I will essentially have sort of n equally spaced vectors, which will always add up to 0.
Okay, okay. So basically, when we turn around to the same vector after a shift of 2 pi, you'll get the same value, and then
Exactly. So it will come back after n, when n goes from this, and I'm equally sampling it. So therefore, it's some. There are various ways to prove this. You guys should take some time to just think and convince yourselves that this equation is true. At the end of the day, it is just this equation and this equation here. This one. If you understand these two, you're done. There's nothing more than this in Fourier analysis. So take your time and convince yourselves of these two. Everything else will fall in place. Okay? So I won't spend more time on discrete Fourier series right now because we'll get to it later. Just wanted to say that all the the properties that we saw in the continuous domain, the continuous periodic signal, they pretty much hold very well for the discrete case as well. The convolution is now called a periodic convolution. You don't need anything other than the n coefficients, right? So it's a periodic convolution over n coefficients, but other than that, it's pretty much the same. And the Parseval's theorem also holds, and it has this sort of nice property that if I take a signal and sum it over n of its values, it's a periodic in n, I can get the energy also by looking at the k coefficients, and now I'm just summing over same n here because the coefficients also repeat after n. Okay, so a discrete Fourier series is periodic in both domains. In fact, we will see this interesting thing that, so Fourier series, I'll just write it here. So this is so time and frequency. So Fourier series is continuous in time but discrete in frequency. Discrete Fourier series is a periodic in time. I guess, yeah. So it's actually discrete and discrete. So, but it's also periodic, and Fourier transform becomes continuous in both. And discrete time Fourier transform is discrete in time but continuous in frequency. Okay, so at the end of the day, once we cover this, you will see such a beautiful symmetry and this complementarity that it will just please you a lot. But there's a bit of slightly different variant, so it's easy to get lost in this. So this is continuous in time and discrete in frequency. This is discrete in time and discrete in frequency. Sorry, this is discrete in time and discrete in frequency. Continuous and continuous. We will do this Fourier transform in the next class. And this is discrete and continuous. So you get all variants when we go through all of this. But we'll get to it. Please read Oppenheim and Wilsky. We're done for the class today. I understand it's a little bit confusing, but it's no easy way to, you just have to spend time on this to make sense, for this to make sense. Okay, so we'll continue from where we left off. I will stop recording and take questions. You guys are, if you have other things to do, feel free to leave now.